In the last episode, we built a semantic search engine by looping through a Python list. That works fine for 5 documents. But what happens when you have 5 million? You cannot loop through 5 million vectors on every single query. That would take minutes. This is exactly the problem that vector databases solve. Our loop from episode 1 compares the query embedding against every single stored vector one by one. With 5 documents, this is instant. With 50,000 documents, the user starts to notice the wait. With 5 million documents, you are looking at minutes per query. This is called brute force search, and it simply does not scale. We need a data structure that can find the closest vectors without checking all of them. A vector database is a database built specifically to store and search embedding vectors. Instead of scanning every vector on each query, it builds a special index that lets it jump straight to the closest matches. It returns the top results in milliseconds even across millions of vectors. You can also store metadata alongside each vector, like the source document name or a date, and filter by that metadata at search time. The most common indexing algorithm is called HNSW, which stands for Hierarchical Navigable Small World. It builds a multi-layer graph where each vector is connected to its nearest neighbors. At search time, it starts at the top layer and navigates downward, narrowing in on the closest matches layer by layer. It does not check every vector. It finds approximate nearest neighbors, which are almost always good enough for search, and it does so in a fraction of the time. The 3 most common options are Chroma, FAISS, and Pinecone. Chroma is open source, runs locally, and is the easiest to set up. It is perfect for learning and development. FAISS is a library from Facebook that is extremely fast and runs entirely in memory. It is great when you need raw speed and are comfortable managing infrastructure. Pinecone is a fully managed cloud service. You do not run anything yourself. It is the easiest path to production, but it does cost money. Let us set up Chroma. After installing ChromaDB and OpenAI, we import both clients. We create a Chroma client and then create a collection. A collection in Chroma is similar to a table in a regular database. It holds a group of related vectors. We give ours the name ragdocs. From this point on, we can add vectors to it and search it. To add documents, we first generate an embedding for each one using the OpenAI model from episode 1. Then, we call the add method on our collection, passing 3 things: a unique ID for each document, the embedding vectors, and the original document text. Chroma stores all 3 together. The ID lets us update or delete a specific document later. The original text is returned alongside results at query time. To search, we call the query method, passing the embedding of our query text and the number of results we want. Chroma returns the closest matching documents along with their distances. Notice the distance for the Eiffel Tower document is 0.08, very close. The Python document scores 1.21, much further away. Lower distance means higher similarity. Chroma handled all the indexing and nearest neighbors search for us automatically. One of the most powerful features of vector databases is metadata filtering. When you add documents, you can attach a dictionary of metadata to each one, like the source name or the year it was written. Then, at query time, you can pass a filter, so Chroma only searches within the matching subset. This means you can do things like only search documents from a specific author, or only search content newer than a certain year. You now know why plain lists do not scale, how HNSW indexing works under the hood, and how to store and search embeddings using Chroma. In the next episode, we tackle document ingestion and chunking, how to take a real PDF or web page, split it into the right-sized pieces, and load it into your vector database.